All right, let's jump right into this explainer. Today, we're stepping into the intense training grounds of radiology. If you picture this like an epic, high-stakes anime storyline, well, we are about to master the raw, elemental electrical forces that power the ultimate machine, the modern X-ray generator. As our guide Priya brilliantly points out in the source material, understand the electricity, and the machine makes sense. And honestly, she's spot on. The X-ray machine is an absolute beast. I mean, we're dealing with tens of thousands of volts here. To control it, we really have to start at the very beginning, kind of like a protagonist learning to harness their true power.
So here's our training roadmap for today. First, the forces of current. Then, rules of the circuit. 3, transformers stepping up. 4, semiconductors and doping. 5, directing the flow. And finally, number 6, the electrical machine. Let's get to it.
Section 1, the forces of current, mastering the basic elements. Moving right into our first challenge, we need to understand the sheer physical forces rushing through the wires. You cannot wield the weapon until you understand the energy feeding it.
Now, before you can fire off a blast of X-rays, you've got to understand the raw power you're actually dealing with. Current, which we measure in amps, is the literal physical flow of electrons. But voltage? Well, voltage is that intense pressure, that heavy push that's forcing those electrons forward. Think of it like a high-stakes pipeline, right? The voltage is the immense water pressure threatening to burst the pipes, and the current is the sheer volume of water actually rushing through.
And right at the core of all this is Ohm's law. Voltage equals current times resistance, or V equals IR. In the world of our radiology heroes, Priya and Arjun, this is basically your ultimate foundational technique. It dictates that if you increase the resistance, but keep your voltage the exact same, your current is going to drop. You absolutely have to master this equation because it governs exactly how much energy you're allowed to wield.
But hey, every superpower has a cost, right? And that's exactly where Joule's law comes in. Power equals current squared times resistance. Seriously, beware of this law. When that massive current hits the resistance inside the X-ray tube's filament, it creates this brutal thermal battleground. Our source actually notes that over 99% of the electron kinetic energy turns into pure, blistering heat. Yeah, less than 1% actually becomes the X-rays we need.
Section 2, rules of the circuit, the laws of conservation. Okay, so now that we've got extreme power and heat at our fingertips, we need some unbreakable rules to keep the whole thing from just spiraling out of control.
Arjun, who's totally the analytical tactician of our source text, hits the nail right on the head here. He says Kirchhoff's laws are essential for understanding how complex circuits with multiple components behave. If you want to troubleshoot this massive machine out in the real world, you can't just guess. You need these universal laws of conservation to track every single drop of energy.
So here they are. First, the junction rule. Current in equals current out. Second, the loop rule. The sum of all voltages around any closed loop is exactly 0. What do these guarantees mean for us? It means no charge just magically disappears, and no energy is lost into the void. Whatever electrical force flows into the battle has to strictly equal what flows out. It's the ultimate balancing act. Section 3, transformers, stepping up, ramping up the power. Now, the crucial point here is that a standard wall socket, giving you, about 220 to 240 volts, just isn't nearly strong enough for our ultimate attack. We need to massively level up our voltage. So how exactly do we do that? Enter electromagnetic induction, also known as Faraday's law. This states that a changing magnetic field induces a voltage in a conductor. Guys, this is basically magic in physics form. It means we can transfer and amplify massive amounts of energy between two coils of wire without the wires even physically touching each other. How cool is that? To actually harness this, we use two specific tools. First step, the step-up transformer. This absolute beast violently spikes our normal wall voltage up to a staggering 150,000 volts for the main X-ray tube. But wait, on the other side, we have this delicate filament that just needs to get extremely hot, not vaporized. For that, we use a step-down transformer, which drops the voltage way down but cranks the current high. It's a perfect dual wielding of electrical power.
Section 4, semiconductors and doping, modifying the elements. All right, with our voltage maxed out to 150 kV, we suddenly encounter a new, terrifying enemy, alternating current, or AC. This stuff constantly flips directions and threatens to completely tear our machine apart.
But Priya reveals our secret weapon to defeat this AC chaos. Doping. Quote, doping. That's the key word for semiconductors and radiology equipment. Now, doping here isn't about cheating. It's the deliberate microscopic modification of silicon at the atomic level to completely control how the energy flows.
This is where we literally manipulate matter. By adding a tiny impurity like phosphorus, which has an extra valence electron, we create an N-type material. It's armed and loaded with extra free electrons. Or add boron instead, and you get a P-type material, which is full of positive holes. We are basically crafting the ultimate electrical armor, piece by piece.
Section 5, Directing the Flow, Taming the AC Beast. So let's combine these mutated materials to create the ultimate shield against that chaotic alternating current. When you smash an N-type and a P-type material together, you forge a diode, specifically a P-N junction. This acts as a strict one-way gate. It allows the electrical current to flow freely in only one direction, which we call forward bias, and completely blocks any reverse flow. It forces that chaotic alternating energy to finally fall in line. And what are the stakes here? Literal life and death for the machine. Priya warns us if AC were applied without rectification, the high voltage would reverse and drive current backward, destroying the tube. Just imagine 150,000 volts suddenly slamming backward into those delicate components. It would completely obliterate the X-ray tube in one catastrophic clash. To prevent that explosion, we use full-wave bridge rectification. Step 1, the wild AC current enters. Step 2, 4 precisely placed diodes step up to block any reverse flow. Step 3, through this full-wave bridge, we catch both the positive and negative halves of the AC wave. And finally, step 4, we force them all to flow in the exact same direction, achieving a safe, relentless, one-way direct current, or DC. The beast is perfectly tamed.
Section 6, the electrical machine, the ultimate form. Everything we've learned up to this point now combines into the modern, high-speed digital control circuit.
Meet the transistors. These are the unsung heroes that act as amplifiers and switches, forming the logic gates of modern electronics. Inside a digital X-ray machine, millions of these tiny transistors are firing in mere milliseconds. They use incredibly small base currents to perfectly and precisely command the massive 150,000 volt forces we just tamed. It's literally like a master conductor leading a symphony of lightning. And this beautifully brings us back to our amazing guides from the Radio Talk source material, Priya and Arjun. Just like seasoned veterans broadcasting the secrets of the machine, they have successfully walked us through the entire construction of this digital beast. Let's lock in this power-up with a quick summary, shall we? V equals IR, or Ohm's law, drives our foundation. P equals I squared R, Joule's law, represents the intense heat we absolutely have to manage. Transformers massively scale our power up and down. Diodes act as our shield to rectify that chaotic AC into a focused DC beam. And transformers, they act as the digital brain to control the whole shebang.
So here is the crucial takeaway from all of this. That safe, one-way DC current is now rushing toward the vacuum tube at an astonishing 150,000 volts. We've built the ultimate electrical weapon. But what explosive physics actually happen when those high-speed electrons finally collide inside the vacuum tube? What exactly goes down when they hit the target? Well, are you ready to find out next time?